All right, so I was showing my other class something. So we left off with this like kind of court case analogy, but we were really talking about identifying null alternative hypotheses, finding sample evidence to see can we reject or do we fail to reject certain values for this population mean. And so we'll kind of pick up where we left off there. One thing I want to mention off the top before we dive into material, I'll post an online quiz as soon as I'm back in my office after class. It'll be due before we start class Friday. You'll have a couple questions that just give me an idea about kind of your comprehension of what we're going through today and kind of what I'm going to do kind of leading into the exam. So I think, some of the practice exam questions have things about critical values. Based off of how the first two sections went, I'll probably not do critical values until after the exam, so you can kind of ignore those questions a little bit. We'll really kind of focus on p-values, okay? So that's what we'll kind of talk about today. It'll make a little more sense after today. And I can talk a little bit more about those problems you can kind of ignore on the practice exams on Friday, once we have a little bit more terminology so you know what I'm kind of talking about. So I have that online quiz as soon as we're done with class here, okay? So we have this null alternative hypothesis. We said the alternative hypothesis is always what we're testing for, what we want to find. We then assume the opposite is true, and that's our null hypothesis. So we're going to end up with three different types of hypothesis that we can do. So this mu0 here just is going to be an actual value when we work through some examples. So we're going to either have, we want to test for whether or not the population mean is greater than a certain value, whether or not the population mean is less than a certain value, or whether or not it's anything other than a certain value, or different than, or not equal to a certain value. Okay. So we'll call this, when we have a greater than sign of the alternative hypothesis, a greater than or a right-tailed test. When we have a less than sign of the alternative hypothesis, we'll have a less than or a left-tailed test. When we have a not equal to sign, we'll call that a not equal to or a two-tailed test. So the right and the left tail, those are one-tailed tests. The not equal to is our kind of two-sided or two-tailed test. Okay. So the type of test we have is based off the alternative hypothesis. So notice greater than sign in the alternative hypothesis, so greater than a right-tailed test. Less than sign, less than or left-tailed test. Not equal to sign, not equal to or two-tailed test. Okay. So three different types of tests we can do, and we'll kind of work through all of them today. Not examples, but I'll kind of show you how we calculate p-values and make rejection decisions for all of them. Okay. I think that's all I want to say here. So the next slide, I've got some things that point out. Really, the steps to identifying our null alternative hypothesis. I've got everything set up here for the mean. On Friday, we'll look at examples where we're dealing with the population proportion as opposed to the population mean. So we have to identify what parameter we're interested in. The next thing is going to be determine if we have a one or two-tailed test, because this will kind of alter how we approach our hypothesis, how we determine whether or not we reject or fail to reject the null. And the third step is we need to be careful about that equality. I'm never going to try to trick you with this. So notice here, everything that I do, every example I'll give you in class, every example on the exams or homeworks, I'm always going to phrase it such that the equality won't be on the alternative, the equality will be in your null hypothesis. So just by convention, we typically throw that equality in the null hypothesis. Notice here it's less than or equal to, greater than or equal to, and of course with the two-tailed test, the complement of our alternative hypothesis, if it's not equal to a certain value, the complement of that is that it's exactly equal to that value. Right? So we'll make sure we get that equality on that null hypothesis. Ultimately, it doesn't matter which one we put it on, because if it's a truly continuous variable, the probability of any one value is 0, right? And so it doesn't really kind of change what we're doing with the p-value. I'll try to show this to you once we have a little bit more of a setup of what we're doing with p-values, okay? So we've got these steps. We'll kind of return to this example and kind of identify our null alternative hypothesis, and then we'll look at another example as well. So this was, we said we want to test for whether or not the average ABV of these domestic mass market beers was less than 7%. So if I'm identifying my null alternative hypothesis there, whatever I want to test for is my alternative hypothesis. So it's usually easier to identify that first, right? I want to test for whether or not that average population mean ABV was less than 7%. So that's my alternative hypothesis. I'll assume the opposite is true for my null. Excuse me, which would be what? That it's, yeah, greater than or equal to 7%. Okay. So what type of tailed test would I have here? I always look at my alternative hypothesis. I've got a less than sign. So here I've got a less than, or we will kind of call this a left-tailed test. Okay. So the next example, just so I'm not switching back and forth the slides, I believe the kind of setup is an economist wants to test for whether or not the mean retirement age is different than 67. So there, what would I be testing for? Well, if I want to test for whether or not that population mean retirement age is different than 67, what I'm really saying is it not equal to 67? So I'll assume the opposite is true for my null, which is that it's exactly equal to 67. Right? So here, I'd end up with a two-tailed test. Now, kind of giving a little bit of idea about why we call them like one and two-sided tests. Notice here, if I were to see sample means that were, I don't know, 4.5, 5.5, only values on the left side of 7, right, would go against the null, right? Anything less than 7 supports the alternative, goes against the null. But what if I see a sample mean of 7.5? Well, that's above 7, but that supports the null. So only evidence on the left side of the distribution, or to the left of 7, goes against the null there. That's the only sample means where I might reject the null. Because anything that's on the right side, well, that supports the null. So of course I'm not going to reject it. However, when we have a two-tailed test, well, if I see a sample mean of 73, well, that goes against my null. But also seeing 63 will go against the null. So there, evidence on either side could go against my null hypothesis. So that's kind of why we say like a one versus a two-sided test. Okay. Any questions up to this point? Okay. All right, so when we're looking at our sample evidence, the only way we can reject the null is if what we see goes against it. If something supports the null, we don't have to go through any of the steps that we'll talk about today. We automatically know we'll fail to reject it, right? If my sample evidence supports it, well, then why the hell would I reject it, right? I'm going to actually, we don't like to use the terminology of accept, but you can think about I would accept the null, or really I'd fail to reject it. Does that get your question? If it doesn't support the null, we might reject. We still have to figure out, is it inconsistent enough with a null, right? And I'll reference that later when we're working through something, an example. Okay? So this was kind of, I went through on the slides, right? We could identify the null alternative hypothesis here. We then also did this for this example where I want to test to see if the mean retirement age is different than 67. So different than should always be a clue that you're dealing with a two-sided test, and not equal to signing that alternative hypothesis. Okay. So the next thing we'll talk about is, okay, even if I see sample evidence that goes against the null, and maybe I'll reject, I might make some errors, right? So we're going to talk about the types of errors we can make, and it'll also give us kind of a little bit better understanding of what we're doing here, I think. So we've got type 1 and type 2 errors. So just to like set up what those are, type 1 errors are when we incorrectly reject the null. So this is when we reject the null hypothesis, but it ends up being true. Right? So we see some, maybe we assume the average income in the US is 50,000. We see a sample mean of 75. We reject the null because that's very inconsistent with what we assume to be true. And then somehow we get the population data to figure out, I just had one of those samples that was way far out into that tail of the distribution, right? So I rejected the null even though I shouldn't have. That's a type 1 error. Type 2 error is the opposite. I failed to reject the null even though I should have been. So these are my type 1, type 2 errors are kind of like the opposite of each other. And you can kind of set this up in a matrix. So let's say that the null is in fact true. Well, then I should always be failing to reject it. That's my correct decision. If the null ends up being actually false, well, then I should always be rejecting it. Right? Those are my correct decisions. However, when the null is true, but I rejected it, so I rejected when I shouldn't have been, that was my type 1 error. And then if the null is false, but I failed to reject it, well, I failed to reject even though I should have been, that was my type 2 error. Okay. So I'm going to give you a little bit of idea about how we're kind of making these errors. And then we'll kind of keep moving. So let's say, let's think about the distribution of our sample means here. Okay. They should be normally distributed around whatever that population mean is, right? But I don't have the population mean. I often just have this assumed true population mean. So maybe I'm thinking about income. Let's say I assume that the average income is equal to 50,000. That's my null hypothesis. I then see a sample mean of 60,000. Okay. So that's inconsistent with what I assume to be true. So I assume it's exactly equal to, so the sides don't matter here. It goes against my null, right? It's not 60,000, or sorry, it's not 50,000. I found something different in that. So a type 1 error would be that if I saw this as my sample mean, I say, well, look, I can figure out what the probability that I saw something this far away from that assumed true mean or anything further is. Like I could turn this into a z-score and find the probability. So if that probability gets pretty low, then I'm okay rejecting what I assume to be true. But a type 1 error would be if I make a rejection after seeing this sample mean, and then I end up finding out, well, actually, true mean was what I assumed it to be, right? So I made a rejection even though I shouldn't have been, but it was because I saw a sample mean that just had a relatively low probability of occurring, right? More often than not, if the true mean was 50,000, I would see, values a lot closer, 51,000, 52,000, right? I just happen to have a sample where I had a sample mean value that was a little bit less likely, right? So we will make errors, right? We will see things that, maybe I find this probability and that's like, 0.005. It was very unlikely for me to see it, but, right, it's not a zero probability. So I will sometimes see these sample means where they're very unlikely. So I reject what I assume to be true, excuse me, even though it in fact is true. So that was kind of my type 1 errors. Okay. I'm rejecting even though I shouldn't be. Type 2 errors is a little bit harder to think about, but I think I can give a decent visual here. So, excuse me. So let's do the same setup, right? And maybe I see 52,000 as my sample mean. Okay. Well, I look at this and I say, well, man, the probability that I saw that or anything above it, like, pretty high. Like it was very likely that I saw 52,000 as my sample mean if my null was true. So I failed to reject the null. Remember, what is a type 2 error is when I fail to reject the null, even though I should have been. So a type 2 error would be, I see something like this, I fail to reject that null. I then somehow get my hands on the population data and I figure out, well, actually, the true population mean was something like 40,000. So I should have been rejecting this as the true mean, right? Because it wasn't in fact the true mean, but I failed to reject it because it was relatively close to that. So that would be kind of a visual of my type 2 error, right? You can kind of already start to see what we're going to be thinking about with this assumed true mean value and whether or not we can reject it is this distribution of my sample means. We're exploiting the fact that we know that they should be normally distributed, right? And so that kind of uses stuff we've already talked about. Don't be too concerned without having a perfect understanding of like type 1, type 2 error in terms of like drawing this out. I'm just trying to give somewhat of a visual kind of something that makes a little more sense with just opposed to like a definition of what it is. Okay? And maybe we'll return to this a little bit after we get a little more discussion about hypothesis testing. So this type 1 error, essentially, we're going to end up calling this alpha, right? So my type 1 error, the proportion of times where I reject the null, even though I shouldn't be, we're going to call that alpha. That's my type 1 error. The proportion of times I make this type 1 error is alpha. Now, generally, when we go through these problems, we're going to set alpha. We generally set it at our usual benchmark values that we were using for confidence intervals, which are 0.1, 0.05, and 0.01. That will correspond to making errors 10%, 5%, and 1% of the time. Right? Those are good benchmarks. So we're going to set this, and basically we're going to say, look, if I set alpha to be, I'm going to go back here. So let's say I set alpha to be 0.05. What I'm really saying is, and I'm not explicitly giving a value for the sample mean, but I'm saying there is some cutoff for if I see a sample mean value anywhere in this range, I know that the probability of seeing that or anything further from this assumed true mean, that area has to be less than 0.05. Or the probability of seeing that sample mean, if what I assume to be true was in fact true, is going to be less than 0.05 or less than a 5% chance of occurring. So I'm saying anything that has less than a 5% chance of occurring, I'm okay rejecting the null there. Right? Now, if the null ends up being true, I'll have made rejection decisions that I shouldn't have been making, right? I'll be rejecting when I shouldn't be, whatever alpha is times 100% of the time, right? Or the proportion of rejection errors I'll be making is whatever I've set this alpha to be. Okay? So that type 1 error, we're going to choose that, right? Because I can say, well, maybe I want to be making errors only, proportion of 0.05, or maybe I want to make the proportion of errors 0.01. We can kind of set that threshold. Okay? So we're going to call that type 1 error alpha. Oh, I mean, it's closely related to what we did with confidence intervals, but a little bit different, right? It's just we're using it as kind of a placeholder. If you really wanted to, you could call it beta or whatever other Greek letter you want, but we're just going to kind of use this alpha. And that's not just us, like that's a normal convention in statistics. I'll come back to that slide in a second. I already mentioned this. We're going to use these 3 benchmark values. Don't worry too much about this here. We're not going to focus too much on type 2 errors. The one thing that I really wanted to kind of hammer on in this slide is that one way we can reduce type 2 errors is to take higher sample sizes. So just another example where higher sample sizes are always good. So with type 2 errors, we'll focus a little bit less on them, and we're not really using them as much in this class. I don't know if this is a perfect answer, but a lot of this is a business statistics. So a lot of the examples we look at, we're going to be more concerned with type 1 errors where we're rejecting even though we shouldn't be. Type 2 errors become really important in certain fields. So if you were to take like a biostatistics course, like biology, they would really focus on type 2 errors because in the medical field, you start out assuming people are healthy. And then if you find evidence that goes against that, you can reject that and say that they have certain diseases, right? So think about what a type 2 error would be there. I failed to reject the null, right? So I failed to reject that someone is, I'm testing for whether or not they have a disease, right? And so there I'm assuming that, they don't have this disease. So I failed to reject that. So I'm failing to say that they have it. Well, if I fail to reject that someone, doesn't have cancer and then they end up having it, that's a problem, right? And so they're way more concerned with type 2 errors than when we generally are in kind of more business related or even just general like sociology even related topics. So, all right, so I want to make sure I mentioned that. And then I always kind of think this is like a stupid example to remember type 1, type 2 errors. If I start out assuming that someone's not pregnant, right, that's my null hypothesis. Type 1 errors is when I reject even though I shouldn't be. So if I rejected the null here, even though clearly I shouldn't be, that's my type 1 error. Also can think about like a false positive. Here, a type 2 error is I failed to reject, so I tell them they're not pregnant, even though clearly I should be rejecting. That's my type 2 error or my false negative. So we're not going to do this, But hopefully we can start to see sometimes in this course where like we could like create monster problems where I could do some hypothesis testing, come up with my type 1, type 2 errors, false positives, false negatives. We were using things like that when we were doing Bayes' theorem, right? So like all these things could be connected in like a huge like problem, right? But I'm not going to do that to you. But this is, hopefully we can kind of see some of these things are connected, right? We can have false positive and false negative rates here. All right, a little bit of an aside there. Now we're going to talk about p-values. So we need a statistic to come up with. We said, how inconsistent is inconsistent enough to reject the null? Well, the thing that's going to allow us to see whether or not we're inconsistent enough to be able to reject the null is the p-value. So we're going to have 3 different types of tests. So the first one, I'll set this up. We'll do a right-tailed test first. So we're going to assume the average income in the US is 50,000, right? Actually not 50,000, sorry. Less than or equal to 50,000, right? So the alternative is that it's greater than 50,000. So we have a greater than or a right-tailed test, right? Because only sample means on the right side of this distribution would go against the null. So only sample means on the right side of this distribution, we might, those are the only possibility we have of rejecting the null. Now, not every value on the right side will we reject, but those are the only values that's even possible to reject the null for. So let's say we see a sample mean value of 60,000. Right? We can find the probability that we saw the sample mean that we did, or anything further from that assumed true value, right? The area under the curve to the right of that. The way we can do this is when we have these sample means that are normally distributed, well, we could turn this into a z-value, and then we've already done all that. I mean, from there, we use a standard normal distribution, it gives us the area to the right, so we have to subtract it from 1. But we've done this already. We know these steps, how to find that probability. So what we're going to call that probability, we're going to give it a name, which is the p-value. So what the p-value represents is the probability I saw sample evidence that was as inconsistent with what I assume to be true, or something even more inconsistent, right? Something even further from that assumed true value. Now I say further because for a right-tailed test, that's going to be into that right tail. If I'm dealing with a left-tailed test, it's actually going to be further into that left tail. Because I've got negative positive values, saying less than or greater than kind of switches. But if I always just say further from that assumed true value, doesn't matter which side of the distribution I'm on. Okay? So the p-value, once again, is the probability that I saw the sample evidence I did, or that I saw sample evidence as inconsistent with what I assume to be true as what I saw, or anything even more inconsistent, anything even further from that assumed true value. Another way of thinking about it is, it's the probability that I saw sample evidence, or saw the sample evidence I did, that was as many standard deviations away from that assumed true value, or something an even further number of standard deviations away that went against that null. Okay. Now, how can I find this z-value? We're going to call this our z statistic. Okay. Now, it's going to be something that we've already done, which is just turning a sample mean into a z-value. We said, how do we do that? You take the value for that sample statistic, you subtract the mean of that sample statistic. Well, the mean of my sample means is always just whatever that population mean was. And then we divide it by the standard deviation of our sample mean, which you could do as an intermediate calculation, or if I plug this all in at once, was the original variance of the data I sampled from over my sample size. Okay. Now, the reason why we're not just calling this a z-value, we're calling it a z statistic, is we don't have the true population mean. We're going to be using an assumed true population mean. I'm going to sneeze, I think. Maybe not. Okay. So the reason why we call it a z statistic and not reference it like a z-value necessarily, usually this would represent the number of standard deviations away from the population mean. Our Z statistic really is telling us the number of standard deviations away from the assumed true mean. Right? So once we have that, now we can use the table and find our p-value. Okay. Now, not quite there yet, but you can imagine this p-value represents a probability. So if this probability starts to fall below a certain amount, then we're okay rejecting that population mean that we're okay rejecting that assumed true population mean. You kind of think about it as before I said, when we're setting alpha, what we're really saying is if the probability of seeing the sample mean that we see falls below 0.1, I'm okay rejecting, right? Because it becomes it's unlikely enough that it's probably the case that this isn't the true population mean. Right? So you can imagine we're going to start to eventually compare, does our p-value fall below this alpha that we set? If it does, we're okay rejecting what we assume to be true. Because the sample evidence we saw is so unlikely, it's fallen below this threshold that we set, it's become unlikely enough that we're okay rejecting what we assume to be true because it's probably not true, right? If it was true, it would just be so unlikely that we saw the sample evidence that we did, and so we're okay rejecting it. It's probably more likely the case that the sample mean, that the population mean is something closer to that sample mean that we saw. So that's kind of the setup for a right-tailed test. I'll then kind of go through what a left and a two-tailed test look like. So before I do that, are there any questions here? Has everyone got everything written down that they wanted to at this point? Questions? We'll keep moving. Excuse me. So let's think about how things might look different we just did a right-tailed test. So now I'm going to do a left-tailed test, right? Where we're assuming that the mean is less than 50,000. Right? So the only real difference here, right, is if instead I had a left-tailed test, well, now evidence that goes against the null is only going to be evidence that's on the left side of 50,000 or less than. So I would have to see a sample mean of something like 40,000. Now my p-value is going to be, okay, what's the probability I saw the sample evidence that I did, or sample evidence that was as inconsistent with what I assume to be true, or something even more inconsistent that goes against the null. So now my p-value is going to be over here on that left-hand side. But then the same steps. I turn this into a z-value. I could look up that on the table, find out what that probability is, compare that probability to alpha. All the steps past that are the same. Left-tailed tests are probably the easiest because you can imagine once I turn this into a z statistic and go to that standard normal table, well, now when I look that z-value up, the table just gives me the area to the left. I'm done. For the right-tailed test, if I looked at this up in the table, it gives me the area to the left. To get my p-value, I would have to subtract it from 1. Right? I mean, those are using things we've already talked about with the standard normal distribution, right? Finding areas to the right versus areas to the left. But that's really the only difference between a left and a right-tailed test. I'll point one more thing out here. If assuming that I find sample evidence that goes against that null, right? So I don't find anything that supports it, right? I'm only doing the hypothesis test if I see sample evidence that goes against the null. What's always going to be true about the z statistics for a right-tailed test? If I'm seeing sample evidence that goes against the null, so I'm seeing values on the right side here. Once I turn those into a z-value, there are going to be a certain number of standard deviations above the assumed true value. So my z statistics for a right-tailed test should always be positive. And for a left-tailed test, the only evidence that goes against the null is on the left side. So it's going to be a certain number of standard deviations below the mean. So I should always get negative test statistics there, or sorry, negative z statistics there. Any questions before I keep moving here? All right. The final one is going to be our two-tailed test. So these are probably the tougher hypothesis tests to do because there's one added step that we need to do, which is, so let's say I got this assumed true value, 50,000. Let's say I see that sample mean of 40,000, right? So instead of a left-tailed test, I'm doing a two-tailed test. Well, I could think about, I can find the probability I saw the sample evidence that was inconsistent with the null, or anything that was even more inconsistent. Right? The problem is with a two-tailed test, if I had seen something that was equally as far away from that assumed true value, but on the other side of the distribution, well, now anything in this range would also go against my null hypothesis. Before, if I had seen something on the other side of the distribution here, well, it doesn't go against the null, it actually supports it. So my p-value is the probability I saw sample evidence that goes against the null, that was inconsistent with the null hypothesis. And so for a one-tailed test, I only had to worry about that one side. Now for a two-tailed test, in practice, I'm only seeing one sample mean. Like I'm only taking one sample and using that. So I'm only going to see this sample mean, and I can find the probability I saw the sample mean I did, or anything even more inconsistent with the null, and I can find this area. But this area only represents half of my p-value, because it was equally as likely from that one sample for me to see something that was as far away from that assumed true mean that would have also went against the null on the other side of the distribution, right? Now, I don't see that because I'm only taking one sample, but I know that it was equally as likely for me to see something on that other side. And that would have went against the null. So now I can find the area in my tail, right? Turning this into a z-value. But I have to remember, it only represents half my p-value. So once I find that area in the tail, I need to multiply it by 2. That way I end up with my total p-value. So the added step for a two-tailed test is whatever, so remember, I'm only seeing one sample mean. I turn that into a test statistic, find the probability I saw something that many standard deviations away from the assumed true value or even further. But then I have to remember the final step for a two-tailed test, I need to multiply this by 2 because it would have been equally as likely for me to see something that went against the null on the other side of the distribution. It's just that I only can take one sample, or I only have one sample to base this off. Any questions on that before we keep moving here? We're going to get to an example here in just a second. So put some actual number. I mean, I'm putting numbers to this, but we're not working through like a complete problem. So here's kind of a reference for these p-values just to kind of remember. Now I'm going to show you some mathematical, like, this is the probability that the z-value, the z-statistic is less than, or sorry, greater than whatever value we find from our problem. Don't get too lost in the formulas here, because I mean, it's more so the process of what we're doing to reject the null hypothesis. The only real formula that we kind of use, because we're using a table, so the table is like using a formula, they're doing the integration for us, but the only real equation that we're using in the process is going to be that z-statistic formula, right? So if it's easier to think about, like just in words, like left-tailed test, find the area to the left of my test statistic, or my z-statistic. Right-tailed test, find the area to the right of my z-statistic. Two-tailed test, well, it depends, because I could see sample evidence that's on the left or on the right. So for my two-tailed test, my z-statistic could be positive or negative, right? So whatever side it's on, look for the area it's into the tail, right? Plot your test statistic, z-statistic, look for the area into the tail, right? And then for two-tailed test, multiply it by 2. Okay? So we already kind of stated our ultimate rejection decision then is going to be, is our p-value less than the alpha that we set? Now, in practice, we can test against all alphas. Like, let's say I find a p-value of 0.03. So let's say I come up with this p-value and it's 0.03. Now, maybe I was given only one alpha, like 0.05, and I could test against that, but I could do all of them. If I'm doing one, I might as well do all 3. Think about like here's my alpha values I could set. And maybe it's easier to think about why we would want to do this, because they correspond to different levels of confidence. So here I would check if the p-value is less than alpha, right? Then I would reject, right? So is 0.03 less than 0.1? Yep. So I can reject with 90% confidence. Is 0.03 less than 0.05? Yeah, so I can reject with 95% confidence. It's not less than 0.01. So I would say here, I fail to reject that null with 99% confidence, right? So I can just test against one, but I mean, I don't know, if I'm doing one, I might as well do all three. So often, like on the exam, I won't just give you one alpha, I'll ask you to test against all three. Like what levels can you reject a null at? Right? In this case, alpha is a 0.1 and 0.05 or 90 and 95% confidence. Okay. Any questions there before we keep moving? All right, let's actually jump into a problem here. So I've got kind of a summary with on a table as opposed to kind of graphically, on a visual, but it's all saying the same information. I think at this point, I want to make sure we can get completely through a problem. So here's our steps, right? Identify the null alternative, figure out if we have a left, right, two-tailed test, choose alpha, or we could test against all three levels of alpha. Then calculate our test statistic from our sample mean in this case. Once we have that Z statistic, look up, use the standard normal distribution to look up what that p-value is. Final step, compare our p-value to alpha. If it's less than alpha, we reject. If it's not, we fail to reject. So let's go back to that original example. We started out talking about hypothesis testing, so these mass market beers. So I've got a sample mean, I've got a sample size, I'm testing for whether or not it's less than that 7%. I'm then given a population variance. So just like with confidence intervals, there's three types of problems. We have a sample mean, and somehow we have a known population variance. We have a sample mean, and we only have a sample variance, or we can be dealing with proportions. So we got a walk before we can run here. So we'll start out with the population variance being given to us. Okay. And I've set the alpha here 5% level or 0.05, but I'll probably end up showing you can test against all three. Okay. So let's just kind of get everything that we know, right? So we go back, we said, all right, I want to test for whether or not that ABV population mean is less than 7%. So I assume the opposite is true, right? That it's greater than or equal to. So what type of tailed test do I have here? I look at my alternative hypothesis. So I've got a less than sign. Yeah, so I've got a left-tailed test, right? Only evidence on the left side goes against the null. So that's the only time I could even possibly reject it, right? You always look at the alternative hypothesis. Yep. Like sometimes, I mean, that's how I remember it, because it's just like easy, like, oh, there's a less than sign, less than left-tailed. You can also think about it as, well, what side of the distribution would there be evidence that goes against the null? Well, if it goes against the null, it supports the alternative. They're complements. So you can think about it either way, but I think probably the easier way, what signs in the alternative hypothesis? Yeah. So I then had a sample size of 36. We were given a population variance of 1. Okay. So if what I assume to be true is in fact true, right? So I've got greater than or equal to 7. Where are we on time? All right, we should be okay. One thing I do want to mention at this point. So I'm always using like the value from my null alternative hypothesis here as the assumed true value, but no one's asked me this yet today, but like I'm really assuming it's greater than or equal to. So why am I choosing 7 and not 7.3 or 8.4? Well, think about it this way. If I can reject that it's greater than or equal to 7, then I can definitely reject that it's greater than or equal to 8. So if I can reject this value, I can reject every other value that's above it. So that's why we're using that kind of lowest value in that range. So, excuse me. So we've got our sample mean of 4.5 here. So we've got a left-tailed test. So what's the probability we saw sample evidence that was as far away from that assumed true value that we did, or something even further into that left tail? That's going to represent our p-value. Okay. So the next step is calculating that z statistic. Right? So we said we'll take the sample mean, subtract the assumed true population mean, divide by square root of the population variance over our sample size, which remember, this denominator represented that standard deviation of the statistic that we were looking at. So at this point, it's just a matter of plugging our values in there to get our z value. So it's what? 4.5 minus 7 divided by the square root of, nope, not 36, 1 over 36. Right? I think if we do this, we end up getting negative 15. Right? So this is pretty wild. If I turn this value into my z statistic, I get negative 15. Okay. Now, as we're getting more familiar with the standard normal distribution, this should raise eyebrows because where does my table stop? Oops, sorry, negative 15 there. This should raise some eyebrows because my table stops at negative 3.99. So the probability I see something about 4 standard deviations away is already basically 0. So what's the probability that I see something 15 standard deviations away or even further? Well, that's just going to be even more closer to, even closer to 0, right? Even more approximately 0, I guess if you want to say it that way. So I end up with this p-value that's basically 0, right? So this is an easy one, right? This sample evidence was so inconsistent with what I assume to be true that if I think about checking, well, is the p-value less than alpha? Well, it doesn't matter. I could test against all 3 here. If my p-value is approximately 0, it's going to be less than all of these. So I can reject at all levels here, right? Because I ended up with a p-value that was just so low. The probability that, so another way to think about the p-value here. What the p-value is telling me is that if what I assume to be true is in fact true, the probability of seeing the sample mean that I did is so incredibly low that there's almost no way that I could see this sample mean if this was in fact true. So because there's like almost no probability I could have even seen this sample mean if this was true, it must be more likely the case is that the true mean is something much closer to that 4.5. So because it was so unlikely, I'm okay rejecting that as that assumed true value as the true value.
So the whole point of this, maybe everything to the sample, you found that a mean is 4.5, but that's really rare, and that's what you're trying to prove.
So what I'm saying is seeing that 4.5 would be very, very rare if what I assume to be true was in fact true. So my sample mean wasn't 7.0. I was just assuming, right? So I didn't have any, I didn't have any data yet. Like this is just maybe what I thought. Yep. That's so inconsistent. Well, I assume that I must have been wrong, right? And that's what we're trying to do. We're trying to say, look, I can assume that it's this value, but based off the sample evidence, I can rule that out. Like I assumed it was 7, but after seeing the sample evidence, I can rule that value out. That's kind of what we're doing with confidence intervals, remember? We were saying anything outside this we could rule out. Well, now we can rule out certain values, but we have an intensity, right? This p-value is so close to 0 that I can say, well, man, 7 is, there's no chance that that's true mean. And maybe I do a different value. Maybe I assume it's greater than or equal to 5. Then I come up with a p-value, and maybe there it's like 0.07. So maybe I can still reject it, but I'm not nearly rejecting it as strong as I was rejecting 7. So that's why hypothesis testing are a little bit more beneficial than confidence intervals, because it allows me to give this like intensity of rejection, if you want to think about it that way. Yeah. Exactly. Yep. Sorry, I just got like really hyped about that, but that was a really good question. Like it's like the broader concept of what we're doing is really important. If you lose sight of that too much, like and get lost in like the steps, you're gonna be like, you can make some really easy, stupid decisions where it's like, well, just think about it. Like 4.5 is not that close to 7, right? And in fact, if the original variance is 1 and then we're dividing, this standard deviation is so small that even if we were relatively close, we could still be a large number of standard deviations away. All right, so we've got our rejection decision. This example is kind of extreme, right? It's more likely that we're going to see p-values that are not approximately 0, like 0.05 or 0.032. And then it gets a little bit more interesting, kind of like the one that I showed you earlier, where maybe we can reject at some levels, but not at all. Right? So I think, where are we at? So I had some, this is basically what we worked through. I've got some snarky hipster meme here, but I think what we'll do on Friday, so I can keep every section together. We went through things a little bit quicker. I think you guys sometimes benefit from the fact that by the time I get to you, I'm realizing maybe ways that weren't as efficient or didn't work as well. So you probably get a better explanation than the other sections. But we'll do another example where we look at these sample means, but then we're going to transition to how do we do the same thing, but for proportions. It's going to be very, very similar. Just like when we were calculating the z value for sample proportions, our z statistical equation will be a little bit different. But other than that, all the steps will be the same. I'll probably even then introduce some examples where we only have sample variances, and then we'll kind of save critical values and kind of some review for what we do on Monday, preparing for the exam that's on Wednesday. Okay. So look for that online quiz to be posted here in the next 5-10 minutes. We'll be due before we start class on Friday. Other than that, enjoy the weather before it starts pouring down rain, and I will see you guys on Friday.